Why does memory thrashing impact OS performance? Have you ever noticed your computer slowing down when you have too many applications open? This slowdown can often be traced back to a phenomenon known as memory thrashing. So, why does this happen, and how does it affect the performance of your operating system? Let's break it down. Memory thrashing occurs when an operating system spends more time swapping data between physical memory, also known as random access memory, and secondary storage, like a hard disk, than executing actual application code. This situation arises when the total memory needs of all running processes exceed the available physical memory. When this happens, the operating system is forced to constantly handle page faults, which are requests to load data from the disk into memory. This excessive swapping leads to a significant slowdown in processing speed and reduces system responsiveness. To understand this better, let's look at some key concepts. Physical memory is the fast memory directly accessible by the central processing unit. Virtual memory, on the other hand, extends physical memory by using disk space to simulate additional RAM. When physical memory fills up, the operating system moves inactive memory pages to the disk to free up space for active processes. A page fault occurs when a process tries to access data that is not currently in physical memory. The operating system then has to retrieve this data from the disk, which is much slower than accessing RAM. Each process has a working set, which is the set of memory pages it actively uses. For optimal performance, the operating system needs to keep these working sets in physical memory. When the combined working sets of all processes exceed the available physical memory, thrashing occurs. The operating system spends so much time swapping pages in and out of memory that it cannot effectively execute process instructions. This leads to severe performance degradation, as the central processing unit becomes occupied with managing page faults and swapping operations instead of running applications. Additionally, as disk activity spikes due to frequent swapping, central processing unit utilization can paradoxically drop. This is because the central processing unit is waiting on slow disk input and output operations, which reduces overall throughput. In extreme cases, thrashing can even lead to system crashes or freezes as the operating system struggles to allocate memory efficiently. Different operating systems handle thrashing in various ways, depending on their memory management strategies. Major operating systems like Microsoft Windows, Linux, and macOS utilize virtual memory and page replacement algorithms to manage memory. However, their effectiveness can vary based on system configuration, workload, and available RAM. To reduce thrashing, there are practical approaches you can take. Increasing physical memory can help, as more RAM reduces reliance on disk swapping. Adjusting the number of active processes can also keep working sets within physical memory limits. Optimizing page replacement policies and prioritizing memory allocation for high-priority processes can further improve performance. In summary, memory thrashing significantly impacts operating system performance by overwhelming the system's memory management. This leads to excessive paging activity that slows down processing. Understanding memory thrashing is essential for managing system resources effectively and ensuring smooth application execution.